Hey, welcome back to lecture 8.3. Okay, with hearing, the magic happens on the basilar membrane. I've got a picture of it here, and what you can see about the membrane is that it contains the hair cells, so those little blue ovals with the little hairs, tufts of hairs coming out of them. Those are the hair cells. And what happens when sound goes through the cochlea, remember that's a fluid-filled sac, the basilar membrane in between the two halves of those water balloons, if you will, that membrane moves around. And as the membrane moves around, the little tufts of hair that you can see right here, those little tufts of hair bend. And it's the physical bending of the hair cells that causes or creates action potentials. That's the deal. That's where hearing really happens. You've got about 16,000 hair cells, and they're distributed along the length of your basilar membrane. And when the rocking happens, the cells bend, just like if I were to take a toothbrush and hold down the top and push the bottom. Actually, why don't I do that? Bend, right? I'm bending the hairs on a brush. It's that bending that the hair cells do that causes the creation of action potential. So you can think of hair cells as a little bit like a brush. Although a funny looking brush, here are some pictures from an electron micrograph of actual hair cells. On the left-hand side, you can see a cluster of hair cells as they naturally appear in someone with good hearing potential. On the right-hand side is what hair cells look like in those of us who have been exposed to a lot of noise during our lives. So loud noises essentially kill hair cells. So you don't want to be exposed to loud noises, because if you don't have hair cells, then when the basilar membrane moves around, right, it's as if the hair cells can't bend. If they're not healthy and strong and growing straight up like telephone poles, then they can't bend. And if they can't bend, there's no action potentials. And if there's no action potentials being sent to your brain says there's nothing there. Okay, how do we figure out what pitch a sound is? In other words, is a sound high frequency or really low frequency? Right? That's pitch. Most humans who have good hearing, and those of us getting older, you'll see this doesn't necessarily include us, but typically when things are working well, humans are sensitive to frequencies from about 20 hertz, which is cycles per second, 20 cycles per second, up to 20,000 cycles per second. So we need to be able to differentiate between different pitches. And I'm going to tell you about 3 theories that explain or attempt to explain how to do that. And what you'll see is that the first 2 theories sort of explain half the story. And so the third theory is the first 2 theories put together. Okay, the first theory is called place theory. And place theory says something very simple. That different locations on your basilar membrane are most responsive to different pitches or different frequencies. So if you have a very high frequency sound, it turns out that will vibrate the base or the beginning of the basilar membrane the most. If you have a medium frequency sound, then that will stimulate the middle part of the basilar membrane the most. The problem with place theory is it can't explain those low frequency sounds because low frequency sounds, as you can see in the square box there on the bottom, sort of stimulate the whole basilar membrane. So place theory can explain high frequencies and middle frequencies, but not low frequencies. So we need a new theory to explain low frequencies. And that is frequency theory. And I've got a little cartoon here that's not going to work. But the idea with frequency theory is that with really low frequencies, and this can only work with low frequencies. The frequency determines how quickly action potentials are sent, right? How much time there is between action potentials. So, for example, if you're talking about a really low frequency sound, like a 100 hertz sound, then action potentials would be, the rate of action potentials would be lower than if you had, say, 200 hertz sound that would send out action potentials a little faster. So the frequency of the action potentials tells you the frequency of the sound according to frequency theory. The problem is this can only work for low frequencies. So how do we create a theory that explains both? Well, you just have to put together the two frequencies, place theory and frequency theory, and that creates the third theory, which is the one that people use. It's called composite theory because it's a composite of both theories. So composite theory says that at high frequencies and medium frequencies, we rely on place theory, that where the place on the basilar membrane that vibrates tells us what the pitch is. And frequency theory says, nope, it's not the place on the basilar membrane, it's the frequency, the rate of action potentials. And that works very well with low frequencies. So that's composite theory.